Hey, you know what we haven't done in a while? Solved some equations. We've been playing around with radical expressions, doing things with square roots and cube roots and other kinds of roots, but so far we haven't really used any of those roots in equations or problems that we had to solve. So that's what today's section is about. And this is going to be in two parts. Part one, we're going to be solving equations that have radical signs in them. And then part two, we're going to be using the Pythagorean theorem to solve some problems about right triangles. So, on to solving radical equations, that is, equations with roots. If you see a square root sign in an equation, this is how you deal with that. Step one, isolate the radical on one side of the equation. Step two, square both sides, or if it's not a square root but some other kind of root, raise both sides to whatever power corresponds to the index of the radical. Then solve for x, and then check your solutions in the original equation and discard any that are extraneous. Okay, I didn't expect all of that to sink in right now, but let's work through some examples and then we'll come back and look at those steps again and see what we're doing. Okay, first example, the square root of x equals 6. Now remember, our big strategy in solving equations is we can do the same thing to both sides. So if we wanted to undo multiplication, we could divide both sides by the same number. If we wanted to undo subtraction, we could add the same number to both sides. And here, we want to undo the square root to go from the square root of x to just plain old x, and we can do that by squaring both sides. So we do that, we square both sides of the equation to get the square root of x squared equals 6 squared. And the reason that helps is because squaring undoes the square root. The square root of x squared would just be plain old x. Meanwhile, on the other side of the equation, 6 squared would be 36. So it looks like we've got our solution here, x equals 36. Let's check that. If we go back to the equation we started with and put 36 in place of x, here's what it looks like. The square root of 36 equals 6. Is that true? Yep, it sure is. So 36 is the solution to that equation. Now here's a slightly different example. Here the equation is the square root of x equals negative 6. Now here if we square both sides, the square root of x squared would just be x, and the negative 6 squared, negative 6 times itself, is 36. So it looks like we got x equals 36 for the solution. But if we check that in the equation we started with here, the square root of 36 equals negative 6? Well, no, that's not quite right. The square root of 36 doesn't equal negative 30 or negative 6, it equals positive 6. So here, this is not actually a legitimate solution to the equation we started with. What happened is that if x is 36, then on one side we'd have the square root of 36, which is 6. On the other side we'd have a negative 6, and those aren't equal, but when you square them both, they become equal. So squaring both sides can take two numbers that are not equal to one another, because one's positive and one's negative, and turn them into numbers that are equal to one another. That is, they can introduce extraneous solutions. So we call this an extraneous solution. It's a solution that doesn't really work in the equation we started with, and that's something that can happen when you square both sides of an equation. Now, I could have guessed that that was going to happen because look at the equation we started with. We got the square root of something equal to a negative number, and that can't happen because when we write the square root of something, we mean the positive square root, the one that is not a negative number. So right away we could have seen, oh, that's not going to have any solutions. When you got the square root of something equal to a negative number, you can just right away say no solutions. And in all the equations that we're going to deal with, if there's not going to be any solutions, if that's going to be what's going on, you're going to be able to tell once you see the square root equal to a negative number. Right away you can say no solutions. Now, there are more complicated examples of equations where what you start out with, it's not obvious that there's no solutions, but it turns out that that's what happens. We're not going to get into examples that are that complicated in this class, but if you go on to take college algebra, you might see some examples like that. So on to the relatively simple examples that we're dealing with. Now this is the cube root of x equals 6. When we had the square root of x and we wanted just x, we undid the square root by squaring. Here we need to undo the cube root, and we do that by cubing, that is by raising both sides to the 3 power. So the cube root of x cubed would just be x, and 6 cubed would be 6 times 6 times 6, that's 216. And so that would be our solution, x equals 216. And if we check that, if we go back and put 216 in place of x, it says the cube root of 216 equals 6, and that is true. That does check out. The cube root of 216 does equal 6. Okay, let's try another example. Here we have the square root of 2x plus 1, and notice the plus 1 is not under the radical sign, so it's only the 2x that's being square rooted. So square root of 2x plus 1 equals 9. Now, it would be wrong to go ahead and square everything on both sides individually. We are allowed to square both sides if we take each side altogether, but we're not allowed to come through and just square the individual terms that are being added together. So we can't square the square root of 2x and the 1 individually. That's not legal. It would be legal to take the whole thing, square root of 2x plus 1, and square that whole thing so that we square both sides that way. That would be legal, but it would not be helpful, because when you take this whole thing and square it, that means you're taking that whole thing times itself. The square root of 2x plus 1 times the square root of 2x plus 1. And if you multiply that out, like with the FOIL method, here's what you get. Square root of 2x times square root of 2x is just 2x. But on the outside, you get the square root of 2x times 1. On the inside, you get the square root of 2x times 1. So you got 2 square root of 2x's. And then 1 times 1 is 1. On the other side of the equation, 9 times 9 is 81. But that's not helpful because we still have the square root of 2x. We still have a square root in our equation. And so this isn't really any better than what we started with. In fact, it's worse. We haven't made any progress towards figuring out what x is. So here's the right way to solve this. So before I do any squaring, I am going to get rid of the plus 1 by subtracting 1 on both sides of this equation. So if I subtract 1 from both sides, I get the square root of 2x equals 8. I subtracted the plus 1, so that's why I just had the square root of 2x here, and then the 9 minus 1 gives me the 8 over here. Now I am going to square both sides. That undoes the square root. Square root of 2x squared is just 2x, and 8 squared is 64. Now I have one thing left to do to get from 2x to x. You know what that is? Divide by 2. So 2x divided by 2 is x, 64 divided by 2 is 32, and I get x equals 32. And if you go back and check that, if you put 32 in for x, well, 2 times 32 is 64. Square root of 64 is 8. 8 plus 1 does equal 9. So that does work. So now to go back and look at our strategy, our steps that we go through to solve these kinds of equations. Step 1, isolate the radical. Get it so that the square root is by itself on one side of the equation. So in that last example, we had to do that by subtracting 1 on both sides. Then once that square root is by itself on one side, then the next step is to square both sides. If you had a cube root, you would cube both sides. If you had a fourth root, you would take both sides to the fourth power, whatever it takes to undo the root. Then hopefully you have an equation with no more radical signs in it, and you can just go ahead and solve that equation until you get x by itself on one side equal to a number on the other side. And that should be your solution, but you probably ought to check it in the original equation and make sure it really does work. So another example, square root of x minus 1 minus 5 equals 4. Step 1, isolate the radical. We want the square root part by itself, so we accomplish that by adding 5 to both sides. Get rid of the minus 5 with a plus 5. So now we have square root of x minus 1 equals, and the 4 plus 5 gave us 9. Now we're ready to undo the square root by squaring both sides. Square root of x minus 1 squared would just be x minus 1. And over on the other side, 9 squared would equal 81. Don't forget to do it to both sides. Now, what's the last thing we have to do to go from x minus 1 to just x? Add plus 1 to both sides. So then we get x equals 82. And that is the solution. If we go back to where we started, 82 minus 1 is 81. Square root of 81 is 9. 9 minus 5 equals 4. Next example, 3 times the square root of y plus 2 equals 6. We need the square root by itself. Right now it's 3 times the square root, so we undo the 3 times by dividing both sides by 3. Square root of y plus 2 equals 2. Now we undo the square root by squaring both sides. Y plus 2 equals, and then 2 squared would be 4. And then subtract 2 on both sides, and we get y equals 2. And we're done. 2 plus 2 is 4, square root of 4 is 2, 3 times 2 is 6. Cube root of y plus 2 plus 5 equals 8. First thing we want to do is isolate the radical, get the root by itself. So to get rid of the plus 5, we subtract 5 on both sides. Cube root of y plus 2 equals 3. Now undo the cube root by raising both sides to the third power, cube root cubed. So y plus 2 equals, and then 3 to the third power, that would be 3 times 3 times 3, that's 27. And then go from y plus 2 to just y by subtracting 2 on both sides, and we get y equals 25. So that's our solution. If you check it, 25 plus 2 is 27. Cube root of 27 is 3. 3 plus 5 is 8. And how about this? 10 plus the square root of 2x minus 7 equals 9. Start by isolating the radical. We want the square root by itself on one side of the equation. So get rid of the 10 by subtracting 10 on both sides. Then we have square root of 2x minus 7 equals -1. Now, do you notice what's going on here? We've got a square root equal to, it's a negative number. Can that happen? Can we have a square root of something being equal to a negative number? No. So right now, I can see that this equation has no solution because it's got a square root equal to a negative. Now, if we didn't notice that and we squared both sides, we get 2x minus 7 equals 1, then we get 2x equals 8, x equals 4. But if we go back and plug in 4, 2 times 4 is 8, 8 minus 7 is 1, square root of 1 is 1, 10 plus 1 is not equal to 9, so that does not work. It would be an extraneous solution. Okay, see you in part 2, where we talk about the Pythagorean theorem and how that works.